Hello everyone, and today in this video I want to talk more about particle operators. And today my main focus will be on guiding or advecting particles towards a point. So we will create a sphere and we will create some points onto that sphere and we will guide those points towards a point in this 3D space. And we will learn more about velocity, we will learn more about Geo VOP that works in dynamic operators, and we will create the dynamic operators also again. And in this video I also want to talk about POP color. By this POP color we will uh, learn more about some very crucial, very important parameters of particles like life, their age, and how we can use this, and how uh, what is an age which is normalized age and how is it equals to life of the particles. And I guess let's jump into our video. And first we will create some particles. First let's create a sphere. I have this sphere. Okay, this is our sphere and you can see it right here. We have a sphere. You can say this to polygon, and frequency 10 or 5 is more than enough, I guess, for this case. And we have two ways to go into the DOP network and create our POP object and solver. First we can create our DOPNet, or we can create our POPNet. These two are same, but inside this we have a network already for us, especially for particles. We have our POP source, we have our POP object, we have the merge node. This merge node can be used to merge different forces. For example, I have this POP force. I can connect this, and when I go in here I can say 1 in the y direction. So we have a force of 1 value in the y direction. We will see our particles moving in the upward direction, and how it is different than giving them a velocity. Force gives us acceleration also, velocity only gives us speed in a direction. So when we are giving this force, you see these particles have an acceleration. They are moving slow and then they are accelerating. And that's why if we want to have some more control on our particles, then this method is okay. But we have another method, and which is first this is just we have to create our POP solver and POP object. This is the same. This is also a DOP network. So okay, we have this method, and that is Geo VOP. You see, this geometry VOP is similar as the attribute VOP that we worked at the geometry level when we were working with, I guess, our attributes of geometries. And this geometry level, this geometry VOP is similar, but this geometry VOP works in here, dynamic operators, and this depends on time. That dynamic operator is just working on values, but here it is working on the attributes of these particles. But here's a catch, and the catch here is it is depend on time. So if a particle is moving with a velocity in this 3D space, this geometry VOP needs to know what is the values of these particles on each frame. You cannot just say I want value at this frame. No, it depends on each frame here. And I have created some short what's the word, a short difference in this. GeoVOP works in DOP. Here in the DOP runs every simulated step. every simulated step is particle is moving in this direction. It is working per frame. Use previous time step, good for simulations, good for modeling, no memory of the past frame. Here memory is needed, runs once per frame, works in SOPs. This is like this DOP. It depends on time. So we are changing the attributes with time, yes, but there we were reading attributes with time, we were changing those values. So in this geometry VOP, we have these same two nodes. First, geometry VOP global, which is our input. This is our output. And here you have this velocity. When you middle mouse click, you can give this constant, or you can create a constant and connect to this. These are just same. And when you connect this here in the velocity, we have this 3 float vector. It is giving us x, y, and z, a direction, also a magnitude. When I say 1, now these particles have velocity 1. And they don't have any acceleration here because this is just the velocity value, and this velocity value is constant. It is not changing, so there is no acceleration. And we are seeing something like this. We can give this a noise. We can add a noise, not cell noise, curl noise. We can add a curl noise, this, and we can connect this to this, but we need to know about the positions of these particles. You will see something like this, and it is the same as when we created our pop force, but here it is not as the same, but it is kind of same. And how? Because we were using the force, but here we are using the velocity. Their force were changing the velocity, force were inducing the velocity, but here we are giving the values directly to the velocity. Just delete these. Okay, we have our particles on this, and when I go here, you see I have the life expectancy, and we don't see the age here, but we have this life. I will talk about this later in this video, but for now I want to see the source scatter onto the surface, right? We need this, so we have points on this geometry surface. Inside this, today we will work here. Inside this, I want to guide these points, advect these points towards a point. We have these points, and we need to create a point. And go back, we have this sphere. Let's create our point. We have this add SOP node, and let's add a point. We have this point, and you can transform this. You can transform this point, and I want to translate this in this 3D space, let's say y, and in the x. So now this point is here, and give this a null. So we have the output node here, and null I want to say point out, or I can say let's say point out. Yeah, point out. And inside this, when you are here, you are seeing this bar. We are not seeing the dots that we saw, something like these dots that we saw in the attribute VOP. We don't have these dots, but we have this bar and this bar. How we will say which, and like how we'll say from which input we want to read the attributes from. So you have the inputs option, and when you say SOP, you can like assign that SOP we have point out, accept, and here now you can read this point attributes this point attribute from this point out 1. Because how? Because we have connected this path into this input 1 inside this. Let's talk about how we can guide these points towards a point. Let's say, for example, we have this sphere right now and we have some points onto it. We want to guide these points, we want to advect these points towards this point. So let's say you have this point and its position is px, py, pz, and we want to guide this into this x1, y1 and z1. This is our final position. So we have this distance right now. And what we can do here, if we are standing at this position and we want to go to this position, what we need a direction plus a distance. We need displacement. Displacement means direction plus distance. It can be the shortest path. So we are using the shortest path. But if we are standing here, we need how much distance and in which direction. If we subtract p, let's say p, small p, if we capital P minus small p, we will get a vector. And this vector will tell us how much and in which direction. When we minus this, we will get a vector. For example, when you minus this from this, let's say you get x, y and z, you get a vector something like this. So this vector will tell you how much you want to go and in which direction and how. When you subtract this from this, you will get a value. So for example, let's say you are here and here the position is, let's say 2. You want to go to 4, right? So how much is this? So if you say 4 minus 2, you will get 4. So you will say, I want to go 2 in this direction, and here direction because we are working with 1D, and here we are working with 3D. So we have this x, y and z. This will tell you in x direction this much, y this much and z that much. So we will get a vector with the distance and with the direction. So we will get the displacement, the minimum distance from this point to this point when we subtract this point to this point. I guess it's clear. So let's do it here. So we have the point position of this point. Where is that point? We have this point position of this point. So we know that we can see it here. This point is, we can have the point attribute. This will import the point attribute. So we want to read the point position. We have this pt number. Pt number means which point number. It is like the number from the point, like which, if we have 2 points, that means we have 0 plus 1. So this is just the point number. So I can give this a constant because there is 1 point, so its pt number will be 0. And we have this constant and its pt number is 0. We are reading the point which has pt number 0. So we will reading the point position and we want to subtract. This input 1 and input 2 is the point position of these points. So we are subtracting the point position and these point positions. From that point position we want to uh, uh, like guide these points towards. Difference you can say into the velocity, and you will see something like this. You will see now these points have the direction and the distance, and they are going towards this point in this 3D space, right? And what if I want just the direction, not the distance value? So we can do this normalized. So now we only have the direction, and the values are going into the v, which means v here is 1, because normalized, if you're normalizing this vector, that means we are making this a unit vector. Unit vector has magnitude 1 and has the direction. So this normalization here, you see, this is our endpoint. But why these points are going here? Because these points have a velocity, right? These points have a velocity, and they don't have like at which they want to stop, at what distance they have to stop. They are just, we are just giving them the value into the velocity, and these points have just velocity value, and they are going by far. They, when they reach here, they still have the velocity values. That's why they're going there. Then the endpoint here is changing. That's why they are coming back, and we are seeing this weird uh, what's the word, glass R, something like this, right? And what we can do here, this is guiding our points towards this. But what if I want to add a noise here? So to add the noise, what we can do, create a kernel noise here. So go inside this, you have something like this, and just duplicate this so we can have our graph much more clear. And you see we have the point position. And what if I add kernel noise here, the position, and I add this to this input and sum into the velocity, and we will see something like this. So they are going towards this point, and you see here they are making this weird shape. Again, they have the velocity, they are coming back and forth, and they are moving around this point because the endpoint is changing, but they still have the velocity. And we are seeing something like this. I here want to talk about 4D vector noise, because kernel noise is 4D vector noise. You see we have a vector x, y, and z. This is a vector. Noise is values in the 3D space. Noise is filled in the 3D space. So when we are saying that we have the noise value at this point, this is our noise, and these are just values in the 3D space. So when I'm giving this a noise, what is happening here? The point position here, P, it is reading the point position, and at that position it is giving the noise value, and the noise value is going into the input 1. But here we have this vector to vector 4, and this vector to vector 4, what it is doing, it is converting the three component vector into the fourth component vector. And here w is our fourth component, which in this case will be time. And this time here is really important, because when I'm saying I have x, y, and z, and we have time, that means now the noise depends on the time also. it depends on the time also. When we have a time period, let's say 1 to 10 seconds, 2, 3, 4, 5, 6, 7, 8, 9, 10. So now noise values change per frame, like it changes per frame, it changes per second. So noise is just numbers in this 3D space, and this number changes over time, over frame, by seconds. And when I'm saying time, time here means seconds. So now we are reading the noise values. This is the position and what time. Now time is also giving us, it is just to have some more visual interest in this scene. So when I am saying the time goes into the vector fourth, which is our fourth component, and now the noise will be much more different than that, because we are reading the noise per second. Per second, the noise is different at that position. When I'm saying the noise value something like this, something like this, I'm saying 1 second, 2 second, not this, 2 second and 3 second. 1 second noise is something like this, 3 second noise is something like this. And these values are creating this pattern. When you sample those values, you will get this pattern. These values are in a way, so we can have this pattern. And when I'm saying at this point x, y and z, what is the noise values at 2 second, at 3 second, at 1 second? So this fourth component is giving us the time, like this component is time also. So we are sampling the noise values at this time, this position. So when these points are changing their positions, so we are sampling the noise values at their position at a specific time here. And now when I say 24 frame, the time is saying here 24, which means 1 second. And now we are reading the noise values at this time. So when we connect this to this, and you will see something like this. Now they are moving in a very weird way. When I let's say bypass this, you will see they're moving something like this. When I say this, they will be moving something like this, right? And it is like really weird, because skull noise is this weird. And when you play with these, and I see that this analytic simplex noise gives us this result, you can have this result, and these are just values. Let's say simplex noise here, and you will get this value here. This noise is like giving some values, and it is a vector. It is a vector, and this vector is adding, we are adding this vector into this direction, right? And that's why we are seeing this, because at each point we are adding some vector. If you see this vector and the noise vector is something like this, so we will get like we will get what's the word, we will get a final vector. And here the values are going into the velocity. We are seeing something like this. You will see we have this weird ball shape. Again, what is happening here, let me tell you this also. What is happening here, you see we have this point, these particles moving towards this point. So when I say this particle is going here, it still has velocity. It still has velocity. It will move far from this point, and it will read. It will also read the noise value here. The noise is also adding on top of it. So it will move in a weird way, but it will come back and forth to its final destination, and we will get this weird noise, because here particles are not dying. They are moving constant. They are not dying here. And when I mean by dying, what do I mean by dying here? So now let's now let's talk about the pop color here. So here inside this I have created a pop color node, and I have connected this into the merge. And here you see we have this. Let's read it again. We have the pop color, and you see we have something like this. Don't forget to turn your this display points off, because that's how we will see the colors, or we won't see the colors, right? Okay, now I have this pop color node and use the ramp. You see something like this, and just change this to, let's say, Inferno, and you will see something like this. And here what is happening, when you set this Inferno and you say, we are seeing something like this. When you are here, life expectancy is 100, let's say 2. Now I want to talk about what is life expectancy and what is age. Life expectancy is the total life of the point. If I am saying life expectancy is 2 here, that means 2 seconds. Here the points will die after 2 seconds. When I say life expectancy 4, these points will die after 4 seconds. So this is the total lifespan of these points. And we can decide here how long these particles will live. If I'm saying 1, life expectancy 1, you will see these colors also, and they will die after 24 frames. You will see these particles will die. 24 here, because 1 second is 24 frames here, and these will die. And why we are seeing this color? First, I have talked about life expectancy. This is our life of the particles, how long they will live. I want to talk about the age. So age here is, when I'm saying age is like at a specific point, it's like my age at this time right now. So when I'm saying at 24 frame, what is the age of these particles? I will say 1 second. When I go to 48 frames, I will ask again, what is the age of these particles? I will say 2 seconds. So age is the seconds, how long these particles have lived already. When I'm saying 72, the age is 3, 96, the age is 4 seconds here. And life expectancy is how long they will live, and age is how long they are living. So we have this an age. An age here means normalized age. So normalized age here, when we normalize a vector, you see age is here not age here is not a vector, it's just time in seconds. When I'm saying normalized age, that means the age is being converted into from 0 to 1. This is normalization means converting it into 0 to 1. We have this normalized age. And when I say life here, when I say life here means life here means, when I'm saying the life is 4 seconds, that means the age 0 to 1, the age, how long they will live. And when I normalize the age, this 0 to 1 is 0 means death, 0 means birth, 1 means death here, and this 0 to 1 will be equals to life, which is the total, because 0 1 here is the death of these particles. And when I'm saying 0 to 1 here, that means they will die at 1 and they will born at 0. So an age is the normalized age, which is equals to life, not in value but in percentage. If I'm saying if the particles have lived 50% of their life, we can calculate their age. And when I'm saying the particles have lived 100% of their life, that means the age here, age value here is 1, they are dead. So this ramp, we are saying ramp equals to normalized age. Normalized age here means that this is 0, this is 1, I'm saying their lifespan is this. They will die at this 1 because an age is like equals to life. So if the life is 4 seconds, that means this value is going to be 4 seconds. And when I toggle like play this, what is the life of this? I'm saying the life expectancy is 1 second. That means the normalized age 0 to 1 means the age when they will get here, they will get 24 frames. Their age will be 1 second and they are dying. That means their n age here is 1 second. They are reaching their end here. So this ramp is color according to their age, right? According to their normalized age, which means here when I'm saying the life expectancy is 1 second, so after 1 second their age will be this is 0 to 1. If I'm saying life expectancy is 2 here, and when I go here I'm saying the this 24 frame they are reaching the half of this, and at the 48 frame they are reaching the end of this n age is like life right now. So the weird thing here, it's okay because we know why it is happening, and we are seeing something like this, right? This is really cool. And we have, what if I say just age, not normalized age, just age. This is just age number, so we are saying that 0 and 1, this is just age. So after 1 second the color will be here. You will see after 24 seconds you will see the color. We prefer an age because it is like how it is working right now. These particles are dying at this, so after this color, this point 0 to 1, nh equals to life. And you can understand this if you like think about this clearly or write about this or try to calculate how this is equals to this. You will understand it's not that difficult. We have this range 0 to 1, and this is where like if you want to understand this, first you will get stuck because this is how it works. You will get stuck and then you will try to understand it, but you will understand this. I will try to like tell you how this is happening. And you see this life expectancy of 0 to 1, this is an age, which is life here, because life, when I'm saying 4 seconds, here 4 second is this is the life, and age is normalized age. So after 4 second, when I'm saying 0 to 4, this is age. At 4 second, after normalizing it, you will get 0 to 1, and 4 1 equals to 4 seconds. When I'm saying 0.5, that means its age will be 2 seconds. You understand this? Okay, now I want to talk about this range value. I'm saying that 0 to 1 is the range right now. 0 to 1 is the age right now, and I am increasing the range from 0 to 4. Let's give this 4. So here I want to tell you, just remember this. We are not converting this range, which is 0 to 4 seconds here. We are not converting this into this. So 4 here means 4 seconds. No, it will not mean this. What it means here, we are like we are stretching this range, so we will get 0 to 1, 0 to 1, 0 to 1. So we are converting this multiply by 4. We are converting this into 4, and we are creating this big range here, and 1 here means the 4 second, not this 4 second, right? You understand this? And I will explain it again. 0 to 4, and it is like we are magnifying this 0 to 1 into 4, and this 0 to 1 here is 4 seconds, not this. So here 25% they will die, and you will see this this purple color, not this. And if you say 2, now we will see this half. We are saying this half right now because we are not doubling that. So I guess you understand this, and I guess I will just say this one, and you will have something like this. And if we want to, like, don't want to see this node here, this node like shape right there, what we can do, we can just decrease the life expectancy, let's say 0.9. So they won't reach at that point, they will die before reaching to that point. So you will see something like this. See how cool is this? And if you, and wait a second, if you move this point, let's say translate that is in x, translate this is in x, you will see something like this. Now these particles are moving following that point, right? See, these particles are following this point. You can turn off the grid. So I guess this is it for this video, and in the next video we will talk more about the particles. And until then, take care, and I will see you in the next video.